So we have added some tools to our machine learning probability theory toolbox already, like the law of total probability. And the next useful tool we're going to get to know is conditional probability. And in order to understand conditional probability, let's look at a simple example. Let's again roll a die. Our common sense tells us that each of the outcomes 1 through 6 is equally probable, and that means that the probability is 1 over 6, whether the outcome will be a 1 or the outcome will be a 2, and so on and so forth. But this can change drastically. If someone tells you that the next outcome is definitely going to be even and you trust this person, then all of a sudden 1 and 2 are no longer equally probable. Why? Well, 1 is not even, and so it's no longer possible. The probability, given this oracle, that the outcome will be 1 is suddenly 0. And on the other hand, the probability that you can get a 2 has gone up from 1 over 6 to 1 over 3, because there are just 3 possible outcomes left if you assume that the next outcome is definitely even. So this simple example shows quite some drastic consequences of conditional probability and conditioning on an event. Let's formalize this idea that we can see in this example. So we take two events A and B, and we are going to condition on the event B. And in order to do this, we require that this event B can actually happen. And this means that it has a probability which is different from 0. It has to have a positive probability. And then we define the probability of the event A, given that the event B has happened, as the ratio between the intersection of the two events and the probability of the event we are actually conditioning on. And this formula doesn't tell you much actually, and you can best memorize it with this picture. We have these two events A and B in the left picture, and we can see that A is actually quite likely. It's about half of the points of the outcomes that we can see in omega. But now someone tells us that B has happened. And if we want to know whether A has happened as well, we have to look at the intersection between A and B, and that's the 2 points we can see on the right-hand side. And now it's again simply comparing the still possible outcomes with the wanted outcomes. And that's exactly this ratio that we've defined up here. So P, the probability of the intersection of A and B, this one here, that's the wanted outcomes, and this one here, P of B, that's the possible outcomes. And that's how this formula works. When I started probability theory, I found this formula quite hard to remember, even though it is actually quite simple in its meaning. But eventually I found a way to memorize it much better. And I'm going to show you because I think everyone can profit from this way. And in order to do this, we are going to start off with the probability of A and B jointly. And remember, this is a shorthand notation for the intersection of A and B, the probability of it. And in order to come to the formula that is the definition of conditional probability, we're going to rewrite this. And I'm going to write it down and then I'll explain it. Now look at this equation that I just wrote down. If you divide by P of B, which you're allowed to do, then you arrive exactly up here. Now, why is this easier to remember in my opinion? Well, you start off with a joint one, so you just write down all the events that you have, A, B, and so on, if you have more than A and B. And then what you do is you pull out the B. You pull out the one that you're conditioning on, And pulling out means you replace the comma by this midbar. And then you have a formula that is much nicer to remember. Maybe this helps you to get your head around conditional probability. So this little trick that we use to memorize the formula or the definition of conditional probability, it actually generalizes to multiple sets, and then it's usually called, or sometimes called, the multiplication law. And what did we have previously? Well, we had the joint probability of the two events A and B, and we could decompose them into the conditional probability of A given B times the probability of B. And instead of taking two sets, we can now generalize this to sets A1 through AN. And the only prerequisite we have is that the probability of them all happening at the same time is positive. And then we can do the exact same thing. Let's parse this formula. We'll start with n in this index, and if we have I equal to n here, then we condition on the intersection of all previous events with an index lower than I, and I is n in our case, so we condition on all the previous ones. And then we multiply the next probability, which is the probability of the event an-1 conditioned on all the previous ones, and so on and so forth. And you might see that in the case of I equal to 1, you end up with A1 conditioned on the empty set, because there's no smaller index than 1. And there's a convention which says that this is just the probability of A1. Okay, so maybe this formula is a bit hard to understand. We can just write it down completely, and then it gets a bit more easy to read or easy to remember. So again, we have an here, for example, and it's conditioned on the intersection of all the previous ones. And we do this with all sets, and we end up with A3 conditioned on all the previous ones, which is A1, A2, and A2 conditioned on all the previous ones, which is just A1, and also A1 conditioned on all the previous ones, and by the convention we just made, this is just the probability of A1, because there's nothing left to condition on. So what you do is you fix one of the events, and we started with AN, and then you pull out all the other ones, A1 through AN-1, and condition on them, and then you apply the same trick recursively. So you pull out the biggest index of the remaining ones, AN-1, and then you condition on the rest, and so on and so forth. And there's one important remark here. We did this in the order of the index, because then it's much easier to write down and also to memorize. But in principle, I could also do the following. So I could write P of A3 times P of A1 given A3 times P of A2 given A1 and A3, and then times everything we had previously. So what did I do? I just interchanged the order of A1, A2, and A3. So when I only had these three events left, I didn't pull out A3 first, but I pulled out A2 and conditioned on the other two, and so on and so forth. So these two lines, the last two lines here, these two lines, they're actually equivalent. One is much easier to memorize, but which one you use depends on the task at hand. So which one is more convenient? Which of these distributions is easier? For example, you could have a case where this distribution is much easier than this one. And that's why you might want to interchange the order. So with the help of the multiplication law, we can revisit the law of total probability. We can enhance the law of total probability, actually. And the multiplication law is particularly helpful if you have an event B which has a hard probability distribution. It's hard to express. And what you can do is you can take a partition of all of the outcomes. We know now what a partition is. A partition is a set of sets, so that the union is the whole set and that each outcome of omega is in exactly one of these sets A in the partition. And what you can do is, instead of looking at the hard probability P of B, which is hard to calculate for some reason, you can look at the individual ones. So you look at all the partitions and take the intersection. And with this one, we now know that we can decompose it in this way. So here's a graphical representation of this. You have the whole set omega, which is the black box, and you have a couple of events, A1 through A5. It's a 5 partition with different outcomes in them, and B is in all of them. And maybe for some reason it's much easier to calculate the probability of this part here, which is the probability of B given A1, rather than calculating the full probability of B. And one simple example of when this is useful is the following. Imagine each of these sets A1 through A5 corresponds to a small black box, and you can't distinguish these black boxes. And the black dots, they are actually marbles in these boxes. And the set B is the outcomes where you actually have a blue marble. So the dots in the set B, they are blue marbles. And now you want to know what is the probability that I'm going to get a blue marble given that I choose a box at random and then choose one of the marbles at random. And well, what you could do is you could count all the blue marbles. But what you can also do is, if you know that in each box there's one marble in the first box and 3 marbles in the second box and so on, you can just write this as written above here, and then P of A is the probability that you choose a given box, and that's just 1 over 5 because you pick them at random and you have 5 boxes. And then you can just look at the individual box, and looking at the individual box may be easier than looking at all the other boxes because you have to keep track of what you did in the previous boxes. And this you can apply to much more complicated scenarios, and that's when the law of total probability will show its full force. The next we're going to talk about is Bayes' rule, and maybe you've heard of Bayes' rule already, but Bayes' rule is in principle just another application of the multiplication law. So what does Bayes' rule do? Bayes' rule establishes a connection between two events, A and B, and the respective conditional probabilities. So there is a connection between the conditional probability of the event A given B and the probability of the event B given A. And why could this be useful? Well, we can look at this marble example again from the previous slide. And the question we could ask is, given that my marble is blue, what is the probability it actually came from box 1? Well, if you think about it, it's not so easy to tell this probability straight away. However, it's much easier to calculate the probability that the marble is blue given that it came from the first box. And that's when you might want to turn around these probabilities. But of course you can't just flip them around and it's exactly the same. But they are related. And Bayes' rule or Bayes' formula tells you exactly how this works. So this can be done by this fraction. And the interesting thing here is also that here again we have P of B. And if you recall the last slide, we also had P of B, and we used the law of total probability to calculate P of B. And that's exactly what we did with the previous example. P of B is the probability that the marble is blue, and you can do this by partitioning the outcomes into the individual boxes. And that's often what you do when you use Bayes' rule. So you first apply Bayes' rule, and then you apply the law of total probability to P of B, to the denominator. Again, this is a bit hard to memorize, but if you memorize multiplication law, you can actually do the proof for Bayes' theorem pretty quickly. And once again, you start with a joint probability of A and B in the middle, and then you pull out B on the one side, and you pull out A on the other side. And now, whatever you need, you can divide by P of B to get this, the upper formula, or you can divide by P of A to the other side to get the reverse formula of the Bayes formula. Okay, so now we've learned about conditional probability, and we've seen that it's actually quite useful, and we've seen some implications of conditional probability. Well, one big goal in statistics is that we simplify terms. So we start with a complicated question or with a complicated probability distribution, and then we apply some tricks and some rewritings, and we hope that we end up with a much simpler term. So far, we only did rewritings like the multiplication law or Bayes' rule, for example. But sometimes this is not sufficient. And that's when independence comes into place. Independence puts more knowledge into the system, and it formalizes some kind of dependency or independency between two events. And we call two events A and B independent if their joint probability decomposes into the individual probabilities. And recall the multiplication law again, which said that this one here is actually equal to P of A given B times P of B. And that's why you can equivalently define independence by saying that the conditional probability of A given B is simply the probability of A. Just do a pattern matching between the left-hand side and the right-hand side, and you can see that this is exactly equivalent. Now, what does this mean? Why do we call A and B independent? Well, if the conditional probability of A given B is just the same as the probability of A, then this means that the event A is completely independent from the event of B. So, given B, we have no extra information about A, and that's why we call them independent. And we can define the exact same thing in the conditional case, so we can have two sets A and B, and we condition them on a third event C, and then they are independent if the probability of A and B given C also decomposes into the individual conditional probabilities A and B given C. Now you could ask, why is this useful? Well, I just said you're interested in simplifying terms, and maybe you can think of the probability of A given B, A, B, and C, the joint probability, and then you apply the multiplication law, and you get the probability of A given B and C times the probability of B given C times the probability of C. You can check this. and see if this matches what you learned about the multiplication law. And now maybe you know something about independence. Maybe you know that the events B and C are independent. Now, what have we just learned about independence? Well, if B and C are independent, then we are allowed to rewrite this as the probability of B. And now we have these two individual probabilities instead of this joint one. Joint probabilities are usually much harder. And this way we have simplified terms. And that's why it's useful to use information about independence.